Hello. This in-class activity deals with interval estimation. We know that interval estimation is one important subject of inferential statistics. In inferential statistics, we use information from samples to infer information about the population. And here for interval estimation, we can estimate the mean of the population by using the sample mean. And what this involved is that we collect a sample and calculate the sample mean and use the sample mean to build an interval to enclose the true population means. And this interval can give us an idea of the accuracy and precision of the estimation. We will point out those points during our demonstration. And we know that there are different ways to calculate the confidence interval, and we can use z-scores, we can also use t-scores. Here are several formulas where we can decide which one to use depending upon what we know, what we are given. And we can use formulas that involve t-scores, we can use formulas that involve z-scores, and so on and so forth. The first formula, m is the sample mean plus minus a z-score and multiplied by the standard error. And obviously this formula involves the use of z-scores. We can use z-scores to build a confidence interval when we know the population standard deviation. Here sigma is the population standard deviation. Yeah. When that happened, we use z-score. Also, it doesn't really matter what the sample size is. If the small sample, medium-sized sample, large samples, doesn't really matter as long as we know the population standard deviation. And that is natural because to build a confidence interval with this formula, we need to know the standard error. But according to the central limit theorem, the standard error is calculated by using the population standard deviation divided by the square root of sample size. And therefore, if we know the population standard deviation, we would know also the standard error. So we can go ahead to calculate the lower bound and upper bound of the interval by using this formula. So once again, if we know the population standard deviation, we would be able to calculate an accurate standard error. So we just use the z-score, no matter what the sample size is. But sometimes we do not know the population standard deviation, but we can still use z-score as long as the sample size is large enough. This brings us to the next formula. In this formula, we see the z-score, but also we see an S sub m. This is called the estimated standard error. We use this formula when we do not know the population standard deviation, but we know we have a sample that is large. We have this rule of thumb: when the sample size is larger than 30, we call this a large sample. When the sample size is large, we can calculate the sample standard deviation. S is the sample standard deviation, and we use the sample standard deviation as an estimate of the population standard deviation. And this calculation, where the sample standard deviation divided by the square root of sample size, give us an estimated standard error. So in this formula, we see the use of a z-score multiplied by the estimated standard error. This happens when the sample size is large, for example, larger than 30. But this may not happen all the time. Sometimes we do not know the population standard deviation and the sample size is small. When that happens, we can no longer use z-score anymore. We have to use t-score. So this formula involves use of t-score and estimated standard error. We use this formula when we do not know the population standard deviation, and we use a sample standard deviation as estimate of the population standard deviation, and when the sample size is smaller than 30, we have to use t-score here instead of z-score. And also, to use the t-score, we need another piece of information, the degrees of freedom, which is, in this case, the number of cases minus 1, n minus 1. Okay. So in the past, we learned about the normal distribution and the student t distribution. You have read about this from the class reading material. The t distribution and the normal distribution are both symmetrical distribution. Let's go to this graph. Both symmetrical distribution, but for t distribution is flatter. The normal distribution is more concentrated toward the middle. When the sample size is small, the difference between the normal distribution and student t distribution is very large. You cannot ignore it. But when the sample size increases, the t distribution approach the shape of a normal distribution. Therefore, when the sample size is large enough, the difference between the t-scores and the z-scores is insignificant. That's when we can use z-score to approximate t-score when you have a large sample size. But when the sample size is small, the difference between the t-score and the z-scores is too significant to ignore. Then you just have to use t-score. But with t-score, you also need to know the degrees of freedom. Okay, so we have these three formulas that help us to calculate the lower bound and upper bound of a confidence interval. Let's bring all these ideas into some practice. Okay. Question number 1. For a normal population with population standard deviation 8 and a sample size 10 is taken, and the sample size, sample mean is 52. Okay, sample size is 10 and sample mean is 52. Obviously, this is the case where we know the population standard deviation. And samples seem to be small. But as long as we know the population standard deviation, what score we use? We use z-score. Okay. 1a, build a 90% confidence interval for the population mean. Okay. This is the formula we are going to use, which involves the use of z-score. Okay. So this formula obviously is correct, and then we can just bring in the actual values. Okay. 52 is sample mean and plus minus the z-score. Now this z-score is one that corresponds to 90% confidence interval. Let's go to decide to see how do we find this 1.64, the z-score. Here is the normal table. Okay, we have seen this normal table before. Okay, this is a normal table. And this normal table, we know the normal distribution is a symmetrical distribution. 90%, if you want to have a 90% in the middle, 90% in the middle, and this table show only half of the distribution. Half of the 90% is 45%. So to find a z-score that corresponds to 90%, in this table we need to find a percentage closest to 45%. 45%. Okay. Now you have 45%. 4495, 4505. So it's between these two. So you can use either one. I decide to use this one. So if I decide to use this percentage, and the z-score would be 1.64. Z-score would be 1.64. So the z-score corresponding to 90% confidence level would be 1.64. See, that's how I find that z-score from the normal table. Then multiplied by the standard error. Now, this is a place that I like to draw your attention to. The standard error, not the standard deviation. This is the population standard deviation, but this is the standard error of the sample mean, which is the population standard deviation divided by the square root of sample size. Okay. If you are sure that this is the correct formula, you have brought in the correct values, you complete the calculation. Two calculations. One is a minus that gives you the lower bound. The other is positive here that gives you the upper bound. So complete two calculations and you obtain the lower bound and the upper bound of the 90% confidence interval. And there are three different ways to express a confidence interval. The first way is to place the lower bound and the upper bound in parentheses. Lower bound, the small value goes to the left. The upper bound, the larger value, goes to the right, separated by a comma. Second way to express a confidence interval is to is to use this notation as mu, the population mean, is larger than the lower bound and smaller than the upper bound. Again, the smaller value is on the left, the larger value, the upper bound, is to the right. Okay, let me go back again. Now, the third way to express a confidence interval is to draw a number line. Then you put these two marks here to indicate the lower bound and upper bound. Also put in the actual values there. So three different ways to express a confidence interval. In your assignment, you can just use one of them to express the confidence interval. Okay, so this interval has 90% probability of enclosing the true population mean. Okay, so if you build 100 of such intervals from 100 samples, and 90 of them enclose the true population mean, and 10 of them do not. Okay, so that's the meaning of 90% confidence interval. 1b, build a 95% confidence interval. Now, 1b has a slight variations from 1a. Now we want to build a a different level of confidence interval. We want to be a little more confident that the interval contain or enclose the true population mean. Okay. Again, we use this formula since we know the population standard deviation, but now we need a new z-score. This new z-score should correspond to 95% probability. So now let's go to this normal table. Okay, this normal table, if you want to have 95% probability in the middle, half of the 95% is 47.5%. So in this table, you need to find a percentage closest to 47.5%. You do have this value 4750. So that exactly 47.5%. And this percentage corresponds to a z-score 1.96. So z-score is 1.96. Come back here. Okay. 1.96 multiplied by the standard error. So you complete these two calculations. One time you calculate the lower bound, the other time you obtain the upper bound, then you obtain this interval. And make sure to express this interval correctly. After we calculate the 90% confidence interval and the 95% confidence interval, I like to make a comparison here. I put the 90% confidence interval on the top and put a 95% confidence interval at the bottom. Remember, in both calculations, we use the same sample size. Sample size is 10. With increasing confidence, see, this interval is larger. Why 95% confidence interval is larger than the 90% confidence interval? Look at it here. In both calculations, you use the same sample size, same amount of information. With the same amount of information from sample, if you want to be more confident that this interval has a higher probability enclosing the true population mean, there's no other choice but to make it larger. When you have same amount of information, same sample size, there's no additional information. If you want to be more confident that the interval you build enclose the true population mean, the only way to do that is to have a larger interval. Okay. It's like you lost your cell phone. If you want to find it, if you can try to find your cell phone in a classroom building, or you can try to find your cell phone in the entire campus. And the only way that you are more likely to find your cell phone is to look through the entire campus. That will give you more, likelihood to find your cell phone. Does it make sense? So with the same amount of information, same sample size, and when you want to be more confident that the interval encloses the true population mean, the only way to do it is to have a larger interval. So that's why the 95% confidence interval is larger than 90% confidence interval. If you want to be 100% sure that the interval you build encloses the true population mean, then you just have to build an interval that extend to infinity on both sides. You're 100% sure that this interval is enclosed the true population mean. So, so the higher the level of confidence you want to be, the larger interval that you have to have, given the same amount of information, the same sample size. Question number 2, from a normal distribution with a population standard deviation 8, a sample size 25 is taken with the sample mean 52. Obviously, this is also a question where we have the population standard deviation 8. So this is another question where we should use z-score. Okay. 2a, build a 90% confidence interval for the population mean. We use this formula that involves the use of z-score. But now we have something new here. We have same sample mean, same z-score that correspond to 90% confidence level. But what is new here is the sample size. So when you calculate the standard error is a divided by the square root of sample size 25. And you complete two separate calculations, you obtain the lower bound and upper bound. Okay. Then you proceed to build a 95% confidence interval, and here again, the only thing that changed from the first question is sample size. Okay. Everything else is the same. Okay. Then you complete the two separate calculations and to obtain the lower bound and the upper bound. Now we need to answer 2C. Explain why the interval width differ between 1A and 2A and between 1B and 2B. For a given level of confidence, which case gives more accurate estimation? And what factor is responsible for making that estimation more accurate? Let's first just focus on the comparison between 1A and 2A. Okay. This is a 1A, question 1A. We have a 90% confidence interval. We use sample size 10. Then question 2A, we also have 90% confidence interval, but the sample size now changed to 25. Okay. You see, same level of confidence, but a different sample size. The result is that with larger sample size, the interval now is narrow. The interval is narrow. You have a narrow interval with 90% confidence of enclosing the true population mean. So thus we find the interval width differ between these two questions, 1A and 2A. Okay. Now the question is that which estimation is more accurate? For the same level of confidence, is that the wider interval is more accurate, or the narrow interval is more accurate? Let's go back to the cell phone question. You are looking for your cell phone. If somebody tells you, oh, look for the entire campus, somewhere in campus, go find your cell phone. Or the other person tells you, oh, try to find your cell phone in that particular classroom. which description is more accurate, give you a better idea of where your cell phone is actually is located. The second one, a narrow zone would give you a better idea of where to look for your cell phone. Now, in both cases, you have the same level of confidence. For the same level of confidence, somebody tells you, I'm 90% sure that you can find your cell phone somewhere in campus. Or somebody else tells you that I'm 90% sure that your cell phone is in that classroom. Where would you go to find your cell phone first? You would go to that classroom. For the same level of confidence, a smaller area would help you to more accurately determine where your cell phone is possibly located. So a smaller interval give you the more accurate description of where the population mean is located for the same level of confidence. Okay. Now, what factor is responsible for making that estimation more accurate? Compare this. The only different thing between these two questions is that for this question we have a larger sample size. Larger sample size means more information available. That makes the standard error is smaller. Smaller variations around the mean, so the interval will be narrow, the estimation will be more accurate. So the factor that is responsible is the larger sample size, and that makes estimation more accurate because it brings down the standard error. So a comparison between 1A and 2A really help us understand which estimation is more accurate and what factor is responsible here. For the same reason, the comparison between 1B and 2B help us understand why the 2B has a narrow interval, because it has a larger sample size. Larger sample size makes estimation is more accurate. The narrow interval makes estimation more accurate for the same level of confidence. Okay? So question 2.